Hello students, welcome, good morning. So once again, we were discussing about atomic structure. So in the last class we were discussing about valency. Not valence, rather it's a very wrong thing. We were discussing about the structure of an atom, right? We started with the structure of an atom and the protons, the number of orbits, the shells, the electronic configuration. So all these things we started discussing with the first 20 elements, the octet rule, the duplet rule, which elements follow the duplet rule, the limitations of the octet rule. So all these things we have already discussed in our previous classes. So today we will move on to another with those things only. Also along with further, I'll go on with a much more rather detailed explanation about the electronic configuration and with more examples demonstrating that how electronic configurations can be written and how electronic configuration is a very significant thing, very significant thing in in determining the chemical reactivity of a particular element. Okay, so structure of atoms. The first let's continue with the electronic configuration only. We discussed in the previous class. We have discussed a couple of examples. Today I'll continue with another example. Let us consider silicon. That's an element, silicon. What the atomic symbol is? Si. We know the symbol of this element is Si. This element is having an atomic number. We know that atomic number symbolized by Z. It's having an atomic number 14. Number of electrons 14. Electronic configuration 2, 8, 4. So when you are writing electronic configuration, so along with this electronic configuration, if you can mention that 2, 8, 4 belongs to which particular orbit, it's then that will be much better, much better. Now it's not that if you do not write, then marks will be deducted. It's not that. It's not a deduction of marks. But I want you to demonstrate. I want you to when you will write answers, whoever will read your answer script will be able to understand it. Yes, you have understood the thing. You are specifying that this particular orbit belongs to this particular orbit contains these many electrons, and this particular orbit contains these many electrons. Okay. So based on that, for that reason only, that you know the thing. It's not that you have marked up only, but you know that the logic of filling up orbits. That also you know it. Okay. So electronic configuration 2, 8, 4. Taking another example, potassium. What's the symbol? K. What's the atomic number of potassium? Yes, of course, correct. It's 19. It is 19. What's the number of electrons then? 19. If Z is 19, then definitely number of electrons, that's also 19. The next is, as Y is 19, the same thing. Please, I repeat once again, number of electrons equals to number of protons. Because we know when the atomic number, that's defined, the Z is defined by the number of protons present in the nucleus of an atom of an element. That's the definition of an atomic number. The definition of atomic number is the number of protons present in the nucleus of an atom of an element. Now when we are defining Z in terms of proton, that means it's by default we know the number of protons. We know the number of protons. It's independent. Now also it's the number of protons, it's independent. But number of electrons we need to calculate. We need to determine number of electrons. There is no point. We are not determining how many protons are present in an atom, in a particular atom. We are determining how many electrons are present. And how we are doing that? I repeated this in the previous class also. This one also I'm repeating that since atom is electrically neutral, and protons are having positive charge. atoms are electrically neutral, protons are having positive charge, and that means equivalent amount of charge, equivalent amount of negative, that means opposite charge. If protons are positive charge, equivalent amount of negative charge is present inside the atom, and those are basically electrons. Then how many has to be? It has to be equal in number, and hence number of electrons equals to number of protons. Okay, then it comes the electronic configuration. So what the electronic configuration of potassium will be? 2881. And how that's done? And sorry, 2881. That means KLMN. Electronic configuration 2881 KLMN. Okay. Coming to another few other examples. Let's consider helium. Atomic number, the symbol is He. Atomic number 2. Number of electrons 2. That means electronic configuration 2. Which orbit present? K. Fair enough. Another example, neon. Symbol Ne. Atomic number, it's 10. Number of electrons 10. Then electronic configuration will be 2,8, or you can also write 28 like this way, no problem. Both are correct. 2,8 you can also write. You can also write 2,8 below or beneath or above that one KL. You can also write 2,8, a slight space in between K and L. That also accepted. But if you are not mentioning this orbit, 2,8, it's better to write in that way. Okay, to give the commas. That's also important. So it's 2,8 KL. So K orbit, L orbit. Another example, argon. Symbol Ar. Atomic number 18. Number of electrons 18. Electronic configuration K288 KLM. Right? So by till this much, I think by now how to write electronic configuration of a particular element is clear to everyone. I hope now by this time how to write electronic configuration of an element is clear to everyone. Okay, I hope so. Now can you, with this, are you able to identify any sort of patterns within this electronic arrangement? Can you identify any distribution pattern within the arrangement of electrons? Can you see, can you identify any sort of distribution pattern? Yes. If you notice, just think that K orbit in the first in helium, in neon the L orbit. Now this helium, this is the first orbit and this is the last orbit. This is the first orbit and this is the last orbit in terms of occupancy. I'm discussing about in terms of occupancy. That means though this is the first orbit with helium, K orbit is the first orbit, and that is the last orbit which is occupied, and that is also completely occupied. The first orbit is having a maximum capacity 2, and you can see 2 over there, right? So completely occupied. What about the what should I say? Neon, K and L. K and L. Once again, K orbit, it's having 2 and L orbit 8. So that's also the last orbit in terms of occupancy. I'm talking about last orbit. So the last orbit is completely occupied. This L over here is the last orbit of neon and it's completely occupied. What about argon? Over here the M orbit turns out to be the last orbit which is completely occupied. Completely occupied. Okay? Now since these are having, so what does it symbolizes? Now first orbit is becoming the last orbit. This is the last orbit, the second orbit. That means in terms of occupancy, you can just, if you just listen to this, if you just focus on these words, I'm discussing about the in terms of occupancy. if we judge that which orbit is the last orbit in terms of electron occupancy, then definitely you will say that for helium it's K, for neon it's L, and for argon it's M. So that's the last orbit. Now this last orbit is also can be termed as terminal orbit, but chemically it is called the, so you can see it's marked over there, it's marked over there. So K, L, M, that's basically the difference, the last orbit. So the terminal orbit and this last orbit or the last orbit completely occupied, and this complete occupancy, the last orbit or the shell rather, is called the valence shell. It's called the valence shell. And the electrons which are present in the valence shell, are termed as valence electrons. So valence shell is the last occupied orbit or shell. Valence electrons, the electrons which are present in the last orbit or shell, is called the valence electrons. Now coming to the definition, what is a valence shell now? We need to discuss what is a valence shell. I told you previously also, the terminal or the outermost orbit or shell present in an atom containing electrons. The terminal means the end, or the outermost, that means the last orbit or shell, whichever, present in an atom containing electrons. That is, it's not that it has to be completely occupied. Complete occupancy, it's not the criteria, or rather the condition for categorizing an orbit or shell as valence shell. So completely filled, for example, maximum capacity 2 or 8, this complete occupancy is not the criteria for identifying or signifying or marking a shell or orbit as valence shell. It's not a criteria. So the outermost or the terminal orbit or shell present in an atom containing electrons is termed as valence shell. Example, sulfur. Let's consider sulfur. Over here the atomic number of sulfur is 16. We know that it's 16. The electronic distribution 286 KLM. So which is the outermost element, outermost shell or orbit of sulfur? M. Outermost orbit containing electrons is M, so that becomes the valence shell. So M turns out to be the valence shell of sulfur. M turns out to be the valence shell of sulfur. M is the valence shell of sulfur. Or it can also be said that the third orbit, M shell, is the valence shell of sulfur. Third orbit or shell is the valence shell of sulfur. Now the question is, what are valence electrons now? If we have discussed about valence shell, then what are valence electrons? We need to discuss that. Valence electrons. Now the very simple definition, the electrons which are present in the valence shell is called valence electrons. The electrons which are present within a valence shell is called valence electrons. So the number of valence electrons of sulfur is 6. The number of valence electrons of sulfur is 6. But if I go previous, if you remember, we have discussed about the potassium. The configuration was 2881 KLMN. So which is the valence shell? N. And valence electrons, how many present? 1. The last orbit is the valence shell, or the last shell is the valence shell. We know that's 1. So number of valence electrons in potassium is 1. Number of valence electrons of sulfur is 6. Number of valence electrons in boron, it is 3 valence electrons, because boron, the atomic number is 5. The electronic configuration 2, 3. So the last orbit is, which is occupied, I'm not specifying whether fully or partially, whether whatever the thing is, it's occupied, that correspond to 3, and hence number of valence electrons in boron is 3. Now coming to the question that is how to draw the structure of an atom. How to draw the structure of an atom? That's a very, very important question. Now, we have discussed so many things over here, that what are the different electronic configuration of elements. We have discussed about the various masses. We have discussed about the electronic configuration, the atomic numbers, the mass number. So based on this, we now need to focus that how we can draw the structure of an atom. There's a procedure. If we know that one, it's not a very difficult one. It's a very, very easy thing. If we can understand that simple basics, then drawing the structure of an atom on a 2-dimensional paper becomes simply, what should I say? It's just as easy as solving a class 2 problem by you. It's so easy. Okay, let's proceed. How we can, the question now, how we can go ahead with this, drawing the structure of an atom. The first what we need to do is, let us consider an atom, aluminium atom. We need to draw the question given to us, or you want to draw the structure of an aluminium atom, or the question which has been given to you is draw the structure of an aluminium atom. That's a question, or the question given, or it can be your wish, or that you want to see internally how the structure of an atom looks like from the interiors. So all these things, it can be your wish or some others, but aluminium atom you are having, no problem. The first thing we will write, that is element given. So when you are having this question, first thing, write element given equals to aluminum. Okay, element given equals to aluminum. Along with this, you need to write, I will prefer that if you are able, it's not that only you will just draw the structure of an atom. If you can, along with the structure, the question given, draw the structure of an atom, along with the structure, if you are able to give these informations just on as a side note, your main is the diagram, but along with that, as a side note, if you're able to give this information, then that would be the best part. You have no idea. That's the best thing. That's simply the best way of answering or attempting a question of drawing a structure of an atom. Okay, so what information I will rather suggest you to give? What information? Few things. These atomic number. The first you have given aluminum, and then based on this aluminum element, you are giving what? Atomic number, in bracket Z, you are writing 13. Mass number, in bracket you are writing A, you are giving 27. Number of electrons which are present equal to 13. Number of neutrons, 14. Electronic configuration, 2, 8, 3. Where under 2 you are writing n equals to 1. You can also go for KLMN, but since KLMN, it's better to go for orbit number 1, 2, 3, 4, 5, 6, like that way. It's better. So n is the now orbit number. So 2H3. So the first orbit contains 2 electrons. The second orbit contains 8 electrons, and the third orbit contains 3 electrons. With this information given, your first step will be to draw the nucleus of aluminum atom. After giving this, your first will be to draw the nucleus of an atom. You will begin with the nucleus first. Right, like this way. 13P, 14N. But since you're using this P and N as symbol, so it's better to write what is P and what is N. Mention that one. Where P stands for protons, N stands for neutrons. Or you can also atomic number Z symbolized. So you can also write over there after 13. You can also write 13 in bracket P, where we will understand what P is, a number of protons, whatever, no problem. Over here you can write number of neutrons you have written. Over there in bracket you write a symbol N, capital N, and then write 14. No, not an issue. Now after this, after you have drawn this atomic structure, rather not atomic structure, it's not complete yet. You've just drawn the nucleus of an atom. You've just drawn the nucleus of an atom. Now it's time to draw the orbits. Okay? You will draw the orbits, and then you will fill up the orbits according to the electronic configuration which you have mentioned. So you will fill up the orbits in accordance with the configuration, electronic configuration which you have specified over here, that the first orbit will contain 2, the second orbit will contain 8, and the third orbit will contain 3. And based on the information what you've given, you are just representing that one in the form of a model or in the form of a diagram on a 2-dimensional paper. Okay? Let us take another example. We will now focus on calcium. So element given, calcium. After that, information, atomic number 20, mass number 40, number of electrons 20, number of neutrons 20. Calculation of neutrons, we know that. We know that one, how to calculate number of neutrons. A equals to Z plus number of neutrons. From there we will get the number of neutrons, which turns out to be 20. Electronic configuration 2882. First orbit 2, second orbit 2, third orbit 8, fourth orbit 2. 2882. Then again we will start with the nucleus of an atom, like this way. 2Pn. We know that what P and N is, what they are. We know that one. P stands for protons, N stands for neutrons. And after that, after drawing the nucleus, we will go for the orbits. We'll go for the orbits. The first orbit containing 2, and we will the second 8, the third 8, fourth 2, and we'll just follow the distribution of the configuration which we have, or you have specified as electronic configuration side as a side note, and correspondingly you're drawn the structure of an atom with the shells and the nucleus present. Okay. Now the next is, since we are discussing about atomic numbers, we have discussed about number of neutrons, protons, all these things. The question, and we know that since atomic numbers, change in atomic numbers means the element itself get changed. Can mass numbers alter the property of an element? This is a very interesting question. If you notice that when the atomic number changes, the element itself changes, right? The element itself changes. When the atomic number changes, the element itself changes. The corresponding question is, if mass number changes, will the element change? Can change in mass number alter the property of an element? What is the truth? The truth is yes. The truth is yes. Changing of mass numbers alter the property of an element. Though it's possible sometimes changing the mass number changes the element of also, completely changes the element, but it's also possible the change of mass number will not change the element completely, but rather it will change some of the property of the element. It's also possible. If an element is having multiple mass numbers, then it's possible. Element is having multiple mass numbers, then it's possible. That means same element but different mass numbers. Element with multiple mass numbers? God, it's shocking. An element will have more than one mass number. Same element with different mass number. How is that possible? Is it so? What do you think? Same element with different mass numbers. Are you joking? Of course not. I am not even joking. In the year 1913, this particular person, his name is Frederick Soddy. In 1913, he discovered something interesting, and he found that a single element is responding in that way, which concludes that it is having more than one mass number. And mass number means, different mass number means the number of neutrons will change. Different mass number means the number of neutrons will change. So Frederick Soddy, this person, is a scientist, he was a chemist basically. So this person in the year 1913 observed this, that an element is responding as if, and it's not a one single experiment which he did. Continuous experiments reveal the same result, that one particular element is showing results as if it is having multiple mass numbers. That means neutron number is varying. That was a very interesting and intriguing observation. And later, with the help of a lady doctor rather, and her name was Scottish doctor Margaret Todd, together they coined a term, sorry for the sentence construction, they coined the term, and these sort of elements existence, they termed as isotopes. So isotopes are basically element having same atomic number, same element. So atomic number means same element, but different mass numbers. So now we need to discuss some of the properties of an isotope or isotopes. They are having the same atomic number as that of the parent element. The number of neutrons differ. They are electrically neutral in nature. Isotopes are not charged species. Because why? Because only the number of neutrons are changing, and we know the neutrons are having no charge. So the number of neutrons, if it changes also, since neutrons are electrically neutral particles, so the entire atom will remain same, will remain unchanged. Rather, electrically neutral. Unchanged means in terms of electrical charge, it will remain. There will be no change in the charge of the parent element. Many of the isotopes exist freely in nature, and some in the combined, since they are unstable. Of course, some exist freely in nature, and some exist in the combined. Some exist in the combined form, and why they exist in the combined form? Because they are unstable. It's not that this instability is not because due to their charged species. No, it's not due to the charge of a particular. They are electrically neutral, but due to certain property differences, as said, the properties differ. Due to difference in the properties, their stability gets disturbed, and hence they exist in a different combined state. The chemical properties remains the same as that of the parent element. Chemical properties remain the same as that of the It's not that. So chemical properties remain the same. Some of the physical properties differ. Some of the physical properties differ. The thing is, examples we are having for the start with hydrogen, 3 isotopes. It's protium, deuterium, tritium. You can see H11, H12, H13. Examples in the form of I've written. It's A, M, Z. Where Z, you can know what is Z, you know what is A, you know, and M is the element basically. So the isotopes of hydrogen properly known as protium, deuterium, and tritium. Then oxygen is having 2, rather it's a mistake over there. It's having 3. So O is O16, 18, and 17. And this O17, it's not the occurrence is not so much, but it exists. Carbon is having 3, carbon 13, carbon 12, 13, 14. Chlorine is having 2, chlorine is having, generally we are aware of this, chlorine 35 and chlorine 37. But chlorine is basically, if I go for the actual number of isotopes, chlorine is almost having 23 isotopes. Chlorine is almost having 23 isotopes. So there are much more numbers there. Silicon, it's having probably 25 isotopes. So the popularly known isotopes are listed over here, but less popularly known are not listed, but they're having. So number of isotopes, it increases. Now the question is, what is valency? It's a very important question. What is valency? It's the combining capacity of an atom of an element to form a molecule. That's a very, very simple definition. The combining capacity of an atom of an element to form a molecule is called valency. Example, sodium is having valency 1, calcium 2. That's a very, very simple definition of valency. Or we can also write this definition: the number of electrons donated, accepted, or shared by an atom of an element in order to attain the nearest inert gas configuration for stability. Now, with the help of this last definition, the second definition, we can determine, the valencies can be determined, how it's 1 or how it's 2, or rather 1 for sodium, 2 for calcium. It can be determined based on the second definition. Let's check it out. We will consider atomic number 13. Okay, we know the configuration, we know it's 283. Now, as I said previously, the number of electrons donated, accepted, or shared to attain the nearest inert gas configuration. Now, this 13 lies between atomic number 10 and 18, which is a neon and argon. Neon is an inert gas, argon is an inert gas. Atomic number 10 and atomic number 18. So 13 is in between 10 and 18. 13 is between 10 and 18. But 13 is closest to which one? 10 or 18? 13 is closest to which one? 10 or 18? Now that is, you have got it correctly, that 13 is closest to the 10, and hence 10 is the nearest inert gas. So neon, of course, neon is the nearest inert gas. Now, focusing on neon, what is the configuration? What is the configuration because of neon? We know that configuration of neon, that is 2,8. Now, in order to become 2,8, this 13 should give out 3, and hence the valency of 13 becomes 3. Electronic configuration is 2,8, and hence the valency of 13 becomes 3, because in order to attain the nearest inert gas configuration, that means 2,8, if 13 has to become 2,8, then definitely it has to give out this 3, and hence the valency of element number 13 becomes 3. Okay, let's take another example. Atomic number 8, the electronic configuration 2,6. The nearest, now neon and helium. 8 is lying between neon and helium, right? This number 8, it lies between 10 and 2. Helium and neon, between atomic number 10 and 2. So who is the closest? The nearest inert gas? Of course, it's 10 once again. So, what's the configuration of neon? We know that it's 2,8, and hence the valency becomes 2. In order to become 2,8, now why it's 2? We are having the configuration 2,6. Now if 8 has to become, rather this atomic number 8, if it wants to convert itself into this configuration, wants to have this configuration to 8, then definitely 2 is common, no problem. 6 has to get converted to 8. That's the point. The 6 at orbit number 2 in atomic number 8 is having 6. And what about this atomic number 10 to 8? So 6 has to be converted to 8. How that is possible? So by accepting 2 electrons, so hence the valency of Z equals to 8 becomes 2. So I hope that's clear. Now 2 things related to this, that is 2 terminologies. One is isobars, where it's called the same mass number, elements having same mass number but different atomic number. The mass number remains the same, but the atomic number is different. Such elements, such elements are stated as, but where the 2, 3 elements are, the mass number remains the same, but the atomic number is different. Such elements are called isobars. Example, we are having argon for 1840, calcium 2040, potassium 19. So these are together 40, 40, 40. You can see they are isobars. Nitrogen 7, 14, and carbon 6, 14. So there too are isobars. Nickel 27, 59, cobalt 28, 59. So isobars. Moving on to the next, we are having isotones. Over here, a slight difference between with isobar. That's the number of neutrons are same. That means 2 elements are having same number of neutrons. Whether their atomic numbers are different, their mass numbers are different, but the number of neutrons, that particular number are the same, and hence they are called isotones. Example, boron 512 and carbon 613. If you calculate the number of neutrons, over here is 7. And similarly, with carbon, over here is also 6. With boron, 7 neutrons. And with carbon, it's 7 neutrons. Similarly, sulfur, there is a typing mistake, sorry. It will be 1636. Sorry, it will be 1636. So it's coming 20. Number of neutrons will be 20. And with chlorine, it's also 20. So sulfur, that's just a typing mistake, sorry with that. 17 is written, actually it will be 16, the 1636. So number of neutrons 20, and number of neutrons with chlorine, that's also 20, 1737. So with this, I would like to conclude today's lecture. So I hope you've understood, and we will again carry on with our further discussions on this chapter in our next class. So thank you, stay home and take very good care of yourself. Thank you so much.